No pressure, no pressure. All right, I'm going to start the talk by warning you guys that I am going to be experimenting on you a little bit. So this may not be the smoothest technical presentation that's ever been done, but we'll see how it goes. Um, so what I wanted to talk to you guys about today is walk you through a system failure that we had at my organization probably about 2 years ago. And we got a lot of interesting information that sort of came out of this in places that you wouldn't really anticipate. And I think it's going to dovetail nicely with what Jason's going to be talking about a little bit later. So to sort of set the stage, I'll describe the failure that happened. So an engineer was doing a deploy to our monolith application, and he noticed that the deploy was taking a long time after running database migrations. He ran the migrations, and he said, like, this is taking longer than it should. Important phrase that we'll come back to later. But this is taking longer than it should. He started getting nervous, started getting antsy, and he paged production operations, that's my team, for assistance. So the on-call engineer dialed into the system. We still say dialed. Isn't that weird? Like you have all these weird nomenclatures like pager duty. None of these people know what a pager is anymore. But anyways, ProdOps dials in, starts looking around, and they notice that there is a lot of weird activity on the database layer. Lots of locking, lots of queries executing at the same time, but not really making progress. Shortly after that, Page came to ops, and a bunch of alarms and Datadog started firing, basically letting us know that web nodes were starting to drop out of the load balancer. So we were quickly trying to figure out what was going on as nodes were getting dropped, being replaced, but the replacement was taking too long. Finally, we got the site down alert. There was a lot of heavy database locking, so that forced our troubleshooting back to the database layer. Turns out that there was a migration. The migration was actually blocked by another query, a long-running transaction that had a bunch of locks, which were preventing the migration from executing, which in turn was preventing the web-based traffic from getting through and making database queries, which in turn led to our system going down. And if you've ever worked in a web environment, that this might be a common scenario that you've heard of before, like these sort of cascading failures. But we really wanted to sort of dig in and understand like what all the parts were of the system and how each of them contributed to the failure. So we're talking about inputs, outputs, feedback loops, all of those bits of data, the alerting, the alarms, how quickly we alerted. We really wanted to understand like how we got into this bad scenario. So before we get into that though, I'll set a few definitions, right? And when we're talking about systems, what is a system? For my definition, I'm saying it's a set of connected things or parts forming a complex whole. Now, another interesting part of that is a subsystem is a set of elements, which is a system in itself, but it's also a component of a larger system. And when we talk about those things, we can look at it at different levels depending on how we zoom into the thing, right? So in our example, we're going to zoom in on the database for it as an example, because the database is in itself a very complicated system. But because we've been fortunate to have things like ORMs, a lot of that complexity gets abstracted away from us. And the thing about abstractions is you really don't need to know anything about the underlying technology until things go bad, and you do need to know about the underlying technology. But we're going to call that out specifically so that we understand that every time we're interacting with another service or system or process, that there is more than likely another large complex system at work underneath that, and it's simply one part of this larger system that we're operating with. Failure modes, for our definition, is a particular way in which system degrades or ultimately fails to perform as intended or designed. So in our scenario, we had a couple of different failure modes, right? We had a failure mode where things were just sort of slowing down and the environment was sort of grinding to a halt. But then we also had a failure mode when the system actually went completely down because we had entered this sort of new phase of down during the incident. So paying attention to the different failure modes and trying to understand where we can catch and intervene at different failure modes is going to be critical when we're trying to assess and determine how we can go about making our systems better. So with that, I'll give you a quick introduction, although there's not really much that wasn't covered by Dave. So thanks for the great introduction. My name is Jeff Smith. I work at a company called Centro. We do advertising technology software. So yes, we help follow you around the internet and remind you to buy shoes that you bought 6 months ago. I apologize for that. It is an interesting technology space, though. There's a lot of interesting technical challenges there, but I won't sell you too hard on that. Got a great slide here with all the customers that we work with. That doesn't really matter at this point, but there it is, because quite honestly, it's the Central theme deck. So we'll walk through the failure in a bit more detail. And I'm going to dive into a little bit about how databases handle locking for those that aren't familiar, just so that we're all on the same page. So here's a quick high-level system diagram of our environment. Nothing too fancy, nothing complicated here. This is for our primary application. So just one of our workloads in AWS. But we've got an ALB that load balances to a bunch of web servers. We use Redis for some data storage and some caching. Postgres is our primary database. Those web nodes are in an auto-scaling group. We use RabbitMQ for some message publishing. All in all, not that complicated of a system. So to walk through what was happening, in our environment, we do blue-green deployments. And what we mean by that is, when we deploy new code, we actually bring up new servers on a separate auto-scaling group that will receive traffic from the application load balancer as we begin to migrate traffic to this new live environment. So when we do that, that's actually both components of the system, both our Sidekick servers. And for those that aren't familiar with the Ruby environment, Sidekick is basically, think of it as like a batch processing or a job scheduling arm to the Ruby ecosystem. You can schedule a bunch of jobs to execute. You can do like distributed work queue management, things like that. So Sidekick is part of our deployment process as well. So we'll bring up web servers, we'll also bring up new Sidekick nodes, and then we'll migrate traffic off them. When we run our migrations on the inactive nodes, because those are the nodes that have the new code base. And in this migration, there was an alter table that was run. And the alter table was run against this table auth users. Now, thanks to the beauty of ORMs, auth users gets access way more than it probably should. Predominantly because you have all these different references and different objects, and you end up touching tables with queries that you didn't know you were touching. But suffice it to say that there is a lot of activity on auth users. So running an alter table is a bit of a known situation where we're a little leery of doing it during the day. Now, in this particular scenario, what happened was a user performed an action which created a lot of long-running transactions. And when I say long, I mean like hours long. Basically, what happened was when they executed this action, they were doing it over a large period of time. So that large period of time generated a lot of jobs to basically churn through the expected work request. Now, you may be wondering, Jeff, did you know that you can limit the date ranges for those types of jobs? Yes, I did know that, but apparently the developer that wrote that part for whatever reason didn't, or more likely, product said, well, we don't want to limit users because we want to make sure they can report on everything. It's one of those types of scenarios where like you make a decision when you're small and then you forget about it for 6 years, and then suddenly you're big and a helpful user discovers it and finds it for you. So I'm sure we're all familiar with that to some degree. So with that in mind, I want to go through a little bit of how Postgres locking works so that we can fully understand what happens. So every query in Postgres will generate a lock of some type. different lock types conflict with one another. So if I have a lock that is access share, any other query that has another access share lock can query all day long and there's no problems. But if there's a query that comes in that is an access exclusive and there's another query running an access share lock, well, now we have a conflict. And what ends up happening is when there's a conflicting lock, what happens is the query that's requesting the lock goes into a queue while the other query completes finishing. That queue continues to build, and then once the lock is cleared, we take the next query in the queue and we execute it. We take the next query in the queue, we execute it, so on and so forth. The catch to that, though, is the queue also blocks subsequent locks, right? So if I'm next in line to execute, any query that also needs an access share lock will back up behind my access exclusive lock. And it'll build and it'll build and it'll build. Another key point to this issue was locks are held until a commit or a rollback execute. So if you query table A in a large transaction, and then you go on to table B, table C, table D, every time you're querying that table or querying those rows, you're accumulating locks that you're holding for the entire duration of your transaction. So it's one of the reasons why long running transactions is a little bit dangerous, especially in our environment. So to sort of illustrate it, what happens is we had some sidekick tasks that had a bunch of access share locks going on, and they were running in long running transactions. But then lo and behold, we run migrations, and the migration says, hey, I need an access exclusive lock on this auth user table. Okay, but I can't because Sidekick has a bunch of tasks running. So I go into the wait lock queue. But because I'm in access exclusive, what happens is all these other web requests that were coming in suddenly begin to back up behind my access exclusive request. And unfortunately, every time someone lands on the website, they generate some sort of query against the database, even if it's just loading that sort of main page or attempting to log in. So what ends up happening is all these internet requests are coming into the web tier. The web tier gets a bunch of HTTP requests that it then tries to initiate queries for in the Postgres database. Those Postgres database queries never come back because they're waiting for the lock. And as luck would have it, our application had no timeouts on web requests. So they just stacked indefinitely. Eventually what ended up happening is we ran into connection and port exhaustion. So now the web node doesn't have any more connections, so it can't answer any more requests. One of the important requests, though, that it has to answer is the request known as the health check. So the application load balancer is basically saying, hey, are you alive? And because it's piled up with connections and can't respond because it's waiting on the database layer, it drops out of the load balancer. The load balancer says, oh, you're gone, you're unhealthy. The auto scaling group replaces the node, but it doesn't replace them fast enough to actually deliver and support traffic. It's a terrible scenario. So if we look at our timeline of events, the migrations run, they're running longer than expected. Someone pages tech ops. The deploy team is sort of stuck on the resolution and they need help. The web tier starts to fire alerts. We notice that there's heavy database locking. Eventually we discover that, find the bad query and kill the blocking query so that the alter table can run and then all of the stuck requests behind it can execute. So when we look at this, we say, all right, where are the different places that we can make improvements on this? And there's a lot, to be sure, right? So we started breaking it down into different areas. The first thing was the alter table. DDL statements on a very busy table can be dangerous. And it's not news to us. We've run into issues with the auth user table before. So what do we do about preventing that sort of thing? 2, long running transactions, 4+ hour long running transactions are bad, but it's one of those things that you probably want to have some sort of soft alert on, right? We'll talk about that a little bit more. And then the third, there were no DB timeouts on the web tier at all. So the web tier would just continuously wait forever and ever and ever for those queries, which was making the situation worse. So those were all sort of contributing factors to the failure. So in terms of possible alerts that we could have applied, we could have had an alert for long running transactions, because soft alerts, a soft alert though would be necessary because we really don't want to wake someone up in the middle of the night. Could you imagine getting that phone call like, hey, Jeff, guess what? There's a query that's running long, right? Like, what do you do with that information? You could just go around killing queries, but the reality is you only want to know if it's causing problems. If you've got long running transactions and it's not impacting the system, maybe someone's running a large report of some sort, who knows? So we could create an alert, but it would have to be a soft alert. So it may not jolt us into action the way we might want. Database locking threshold. Maybe we could have alerted on the number of DB locks, which could include the deploy team on something going wrong. And that's another good one. Again, another soft alert though, right? Because a lot of database locking may not be bad, because guess what? An access share lock is still a lock. So we could arguably be alerting because there's a lot of queries going on at the same time, but all those queries are running concurrently. But then as a sort of a nuanced response to number three, we could do an alert on block queries. And that'd be a little bit better, right? Alert when there's a large number of queries are blocked, and life would be good. So we started looking at these things and we said, okay, if we had these things, maybe we could have prevented it. But I'm a bit of a cynic, right? So I started looking at the problem and I said, there's another component to this that we haven't talked about. There's a huge part that is more integral than most people give credit for. And people thought I was crazy when I wanted to drag this out of them. But I said, that component is people, right? There are people that are taking part in this system, and we haven't really addressed or understood any of the problems that they've run into or that they've been encountering during this situation. So let's take a look at the operators, right? The operators are going to be interacting with this system at various points, right? So the question is, how are the operators interacting with the system? How are they manipulating the system? How are they changing the system? How are they getting data out of the system? What knowledge do they have about the system? What is it that they exactly know? And where did that knowledge come from? And more importantly, do they know where to look for the status of the current system? We have a saying at work that I repeat all the time. The absence of errors doesn't mean things are working, right? You can't just look and say like, oh, there's no errors, everything must be great, because a process could be executed and producing the wrong output, but not be generating any errors. If I give you I give my 6-year-old a bunch of math problems, like, yeah, no errors, although, he's not doing the right assignment, right? But he's handing in work. Same thing with our systems. How do we validate that it's doing exactly what we say they're doing and what they're supposed to be doing? So I decided to have a postmortem on the people of the system, and to actually dig into what it was that people were thinking, what they were experiencing, and where that knowledge sort of came from. So the first thing that jumped out at me that I thought was interesting was someone said, the primary person that was on call, or that was doing the deploy engineer, they said it seemed like the migration was running long. What does that mean though? So how did you know the query was running long? And he said, I did the deploy in the staging environment. It only took a second or two there. So when it was going for more than a minute, I figured something was up. And these are all quotes from the actual postmortem. So he did the deploy in the staging environment, and that gave him the context for how long this thing should be running in production. But what if he wasn't the person that did the deploy and staging? Or what if he wasn't the person that did the deploy in production? What if he got hit by a bus after doing the staging deploy and he was sick and someone else had to do the production deploy? So we started digging into that, and we said like, well, that context saved us a lot of time, because someone might have waited a half hour not knowing and said like, things are weird. But because it only took a couple minutes before he said something is weird, we realized that that was valuable context that we needed to be able to share with other deployment engineers. So we started trying to come up with ways that we could radiate that information so that anyone doing the deploy would be aware of that. So we went back and we modified our deployment engine. So we use a chatbot to do all of our deploys. We call him Marvin. So here you can see where, Carrie is executing a platform migration for production on the inactive deployment. So what we added was a brief snippet where we're tracking when a migration is run in staging and radiating that information for the matching deploy in production. So it says, oh, I found one staging migration for this version, and it ran 11 seconds on staging 02 at this date and time. So now we're providing further context that was valuable in one incident to anyone that would do the deploy. So now, regardless if you were involved in the staging deploy, you'll be like, it only ran 11 seconds in staging, but it's been 5 minutes in production. Something might be up, something might be afoot, as opposed to waiting 30 minutes only to find out that we're covered in failure there. Why didn't we catch this in staging? That is a favorite question of management, right? Because staging is everything, right? But we don't have users in staging, was the answer. Also, the sidekick job that was running in production, creating the long-running transaction, was initiated by a user and was kind of an unusual case. It was a perfect storm. And that is something that we've used continuously to beat the drum to everyone that will listen. Staging is not production. I'm not saying that staging environments don't have value. They absolutely have value. But when people say, oh, staging needs to be just like production, it will never be just like production. The only way it'll be just like production is if you launch it on the internet, invite users to use it on a daily basis, and treat it exactly like production. But no one treats staging exactly like production. Therefore, it will never be exactly like production. Again, not to say that it doesn't have value. It has value in very specific contexts, but you have to understand the types of issues that staging can catch and the types of issues that staging can't. And when you're talking about interacting with a user community, a lot of times that's a difficult thing to catch in staging. What inevitably happens is you experience a failure in production, then you replicate that case in staging, but you've always got to experience it in production first, which doesn't save you from the discussion. Why did we need to page ops? It's not like I don't like work, not like I hate being on call, but that was a curiosity to me. Like, what was it that ops had that the deployment engineer at that time did not have? Nobody else has access to the DB at that layer. Plus, we don't have the Postgres knowledge to find blocking queries. I wouldn't even know where to start finding out that info. That's a good piece of data there. Nobody else has access to that DB layer. Now, those are one of those things that, it's difficult to control, right? Like in production environments, you can't just go handing out DB access to everyone, especially in a monolith. Our security team sort of frowns on that. But they really don't need production access to the DB for this necessarily. They really just want to know how they could get blocking query information. Now, the interesting thing is when they came to me about it and asked, everyone assumed that I know how to query for blocking queries. Newsflash, guess what? I don't know how to have a query for blocking queries, but I do have a handy notebook with a pretty cool snippet that will show me blocking queries. So my expertise isn't necessarily in knowing how to execute a blocking query. My expertise is knowing when I should be looking for a list of blocked queries. But they had that information because that's exactly what they wanted to do. So really, you didn't need me, you needed my notebook. So we said, well, maybe we can codify that. So what we did was, going back to Marvin, our old friend, we took Marvin and we built a new command for him so that he can list block queries in production. And here you can see Marvin reports that there are 175 blocked queries. It gives us one of the queries and it tells us the query that is actually that is blocked by it, this alter table command. So funny story. We had a very similar issue maybe 2 weeks after this incident. But this time, the team that was doing the deploy said, wait a second, I remember there's this lock queries command. Let me see if there's any blocking queries because this is running longer than it should. They ran the command, they were able to get the output they needed, and then they were able to terminate the transaction that was doing the blocking so that the alter table could run. It was perfect. They did not have to page ops. They had everything they needed. And while, yes, we still ran into the problem, it empowered the people that were on the ground to fix it themselves. And we didn't have an outage. We had a momentary performance impact, right? But the system never went down. No one had to get paged. And the team was able to do it in a self-sufficient manner. This was one of my other favorite ones. Why wasn't this migration flagged for a maintenance release? Because understand, we know auth users is a difficult table. We know this, we've experienced it before. So usually we flag these types of deploys for a migration, for a maintenance release, in which we take all the sidekick nodes down, do the deploy, do the migrations, then bring the sidekick nodes back up, specifically to sort of eliminate a lot of that contention. The answer was this was the developer's first time really working in the platform. He works on some of our other services, but had never worked on the primary platform app. He wasn't aware of the history or the access contention around this table, and it went smoothly in staging. So I know the developer that worked on this, and I have a lot of respect for him. He's a very sharp guy. So I'm thinking to myself, well, if Kyle didn't know this, there's probably a lot of other more junior engineers that also don't have any idea. So how exactly are people supposed to find out about this? Is it infused in them during the new benefits hire, right? Like, are they going through it in orientation? Like, you know, here's your HR packet. Oh yeah, and here's a list of tables that you really need to be worried about anytime you do a migration. So where does that information come from? So did some asking around, and then I discovered that in our repository, we use this app called WorkZone. We're an Atlassian shop, so we use stash/Bitbucket. So what WorkZone does is you can basically set in a series of like file paths or file regexes, and you can say, if anything matches this regex expression, add these mandatory approvers to the PR. So there are two guys that are automatically added for any migration. And I went to them and I said, hey, you know, you guys looked at this. Were you not worried about the auth users table? And they said, I don't remember seeing this at all. Like, that's interesting. So we dig into it. Guess what? The WorkZone setting configuration had been disabled. Why was it disabled? Well, because apparently a week or 2 weeks ago, prior to that, they needed to get a hotfix out. That was really important. And guess what? The two gatekeepers that have to approve those things weren't available. So they disabled WorkZone so that they could get the hotfix out, but then they forgot to turn it back on. So our gatekeeping mechanism that was supposed to protect us from these terrible things actually enabled a portion of the failure. So we re-enabled that so that they would continue to get added to those PRs. But it gets even better. Gets even better. What was the reason for the schema change? The change was part of an enhancement to force password expiration. It's part of a larger security hardening effort. Wow, that felt cool because I was the one that asked for the security hardening effort. But the interesting thing was, when I made that request and put in that ticket, I thought I would be involved with it. So I wasn't extremely prescriptive. I just said, hey, we should follow some guidelines or something like that. Someone took it and ran with it, and unbeknownst to me, this change was rolled out. Now, the reason that's unfortunate is because had they talked to me, they would have known, or I would have told them, that NIST specifically says verifiers should not require memorized secrets to be changed arbitrarily. However, verifiers shall force a change if there is evidence of some sort of compromise of the authentication. So in NIST's own guidelines, they're saying rotating passwords doesn't work as great. And the reason they say that is because when you rotate passwords, what ends up happening is people write it down or they come up with very insecure patterns. So it's worse. It's better to have a very complex password that you force people to have, but then you don't make them rotate it to avoid the repeating pattern bit. But we could have a discussion about this. But because they sort of went on without me, there was no conversation or no discussion. So was this a technical failure? Because we're talking about a change that wasn't needed, was missed by a review process that was disabled, for a change that couldn't be simulated in staging, that interacted poorly with an unusual user action, which led to a system failure. Is this a technical failure? Is it a process failure? Or is it a system failure? It's all of these components combined that resulted in this particular type of outage. And I'm sure that if we changed one minor detail about any of these particular failures or incidents, the situation could have changed dramatically. But all of these things put together into a cauldron of mischief produced this particular unique failure. But it's important for us to understand that this was beyond just technology. This was people. This was process. We fix some of it with tools, but some of it we have to fix by communicating with each other a little more effectively. So some of the lessons learned in this whole ordeal. One, there is no single root cause. I know this has been popular. We've been talking about it for a while, but it always bears repeating. Always try to dig deeper. There's never, very seldom is there a single root cause. Work in a vacuum is difficult, right? You got to talk with all the stakeholders. The work that was done specifically for the security hardening effort created this scenario where change was done that wasn't necessary. Use automation to free expertise. We have people throughout the organization that have very specific skill sets and sets of expertise. We want to use automation as much as possible to democratize that, to give it to other people without actually requiring that expertise. We do it in automation so that we can do it safely, repeatably, and so that it becomes accessible to more people. Staging is not production. You can make it close, it's a lot of work, but it is not production, and you have to understand what those gaps are. And most importantly, humans are part of the system. Our process can have technical impacts, so we have to understand exactly how we go about delivering software, even the human parts, beyond continuous integration and continuous deployment, but all the way back to that individual engineer that's behind the keyboard typing git commit. Lastly, and I say this all the time, but uptime and stability is a feature, right? This doesn't come for free. We have to work at this. We have to develop this. We know that zero downtime deployments are a thing, right? But that requires a change to our process. It requires a particular set of staging on how we create database migration and schema changes, right? We have to make sure that we're doing it in an additive way only. But that's not something that's just going to come for free. That's not something that we're going to be able to do a bundle install on, right? We have to change our processes, and we have to change how we approach the problem. It's a feature. It has to be worked on. And if you don't have time in your sprints for that, it's not going to show up in your final product. All right, I think I'm out of time. So thanks for having me. Can't wait to get back to Seattle in person, hopefully one day soon. And